Here on Chalk Talk, we've been talking about wide band gap materials for quite a few years. And for some of those years, it was the technology of the future. But now, silicon carbide and gallium nitride are everywhere. The growth in the EV, robotics, and solar and data center markets has gone hand in hand with this technological innovation. All right, long story short, wideband gap material power systems are here to stay. But there is one big design concern that we need to keep in mind when designing these kinds of applications: isolation. Have you heard about reinforced isolation? This kind of isolation technology is a game changer. Let's talk about it. Hi, I'm Amelia Dalton, host of Chalk Talk. Today's smarter power systems demand smarter gate drive isolation. In this episode of Chalk Talk, Kritika Murari from Bourns and I explore the hidden complexities of gate drive isolation, how reinforced gate drive isolation can improve a variety of design parameters, and how you can take advantage of Bourns Push-pull Isolation Transformers for your next design. And before we get started, don't forget to click that link. There you can find even more information about this topic from Bourns. Hi, Kritika. Thank you so much for joining me.
Hi, Amelia. Thanks for having me here.
All right, so we're talking about smarter isolation solutions for today's smart power systems. And we're seeing a fundamental shift in power electronics with a greater adoption of wide bandgap materials. So, how is this changing the trajectory of power system design?
Yeah, I'm really excited to talk about something very crucial for the future of power systems. As you said, we are seeing a fundamental shift in power electronics and distribution. You've probably heard about silicon carbide and gallium nitride FETs, and these aren't just buzzwords, they are setting new standards for switching performance, efficiency, power distribution, power density, and how small we can make things, especially compared to traditional MOSFETs and IGBTs that we've relied on in the past. So these wide band gap materials, they are enabling power conversion modules that are smaller, lighter, and far more efficient. But here's the kicker: unleashing the full potential of these incredibly fast switching devices, especially in applications where electrical isolation is a must. And when I say electrical isolation, we are thinking user safety and protecting smaller, sensitive voltage circuitry. So how does that bring significant design hurdles, and how does that make it more challenging for us to make these power modules more efficient while keeping safety in mind? And that's kind of where smarter isolation comes into the play.
Okay, so for these types of applications that you mentioned, we need robust gate drive isolation, correct? So, what kind of challenges are we talking about when it comes to this kind of isolation?
Oh, you're absolutely right. So, as we push for higher performance for applications in clean energy or applications within a wide range of industries, such as transportation, which goes into electrical vehicles and robotics. So, the challenge lies within the fact that these energy sources, for example, renewable energy sources such as solar, they are less constant, they are less predictable compared to conventional power supplies. And this drives the need for sophisticated smart grid management. And as we push for higher performance within these applications, and especially as we transition towards a microgrid structure with distributed energy sources, the demand for safer, faster, and smarter isolation just keeps growing. So think about it. When you're designing an isolated gate power supply, it isn't just about delivering volts across a barrier. So there are a couple of challenges that you have to think about. So it's about delivering the right power. It has to be stable. It has to be precise. You have to think about power fluctuations. And then you have to think about suppressing electromagnetic interference. This can be a significant challenge, especially when it comes to high-speed switching, which is kind of one of the main pros of these MOSFETs that we are talking about here. We have to consider EMI as a major challenge, which can potentially cripple the whole system itself as well as nearby systems. And then lastly, you have to think about the design trade offs. So these systems, the whole loop, the whole circuitry can be quite complex, and the control algorithm needs a lot more complexity just for stability. And as you kind of dive deeper into these technologies, the topologies get more advanced and complicated as well. So you have to kind of think about what's the trade off and how are you going to find the right balance between signal fidelity, power delivery, and also balance the noise interference.
So, what kinds of solutions does Bourns offer for isolated gate drive?
When you think of isolated gate drive, what's very important is the isolation transformer that actually plays a major role in isolating the power delivery or any parasitic values that come into play here. So, what Bourns has come up with is a transformer that potentially helps solve most of these problems that we've just talked about right out of the box. This is exactly what our SM91243L offers. This isn't just a passive transformer you just drop into a circuit. It's a purpose-built solution designed specifically for engineers who are building tomorrow's isolated gate drive systems. So what makes it special? This is a reinforced isolation gate drive transformer. This was specifically developed for use with Allegro micromodel chipsets. We'll talk about this in a little bit. This transformer, it boasts ultra-low parasitics, high voltage reinforced insulation, which is very important, and incredibly seamless integration with a number of advanced GaN chipsets. These features directly address those critical challenges we talked about, so power stability, EMI, and safety. Plus, it's compact. The whole device footprint is extremely small. We use an automated process to actually manufacture these transformers, which helps to support scalable and high reliability designs, and it's truly built for the future.
So, how does this solution compare to traditional gate drive technologies?
Let's take a moment to kind of compare traditional gate drive versus reinforced isolation gate drive systems, which is what SM91243L is based on. So as you can see here, there are a couple of parameters that we've kind of based the design on. So starting with isolation, which is kind of the main feature here. So if you talk about traditional gate drives, there are multiple components involved in just within the circuitry itself, just for making the transformer properly isolated, making it perform better. But within the SM91243L, this is kind of a compact transformer and it's reinforced, and you don't really need external components for just for isolation. Then when we talk about power delivery, traditional gate drives have a separate isolated DC-DC gate bias, but this transformer has an integrated bias delivery. And then we talk about signal integrity. I've already mentioned that these systems are highly susceptible to AMI, but SM91243L, it offers ultra-low CIW to reduce the overall noise within the system. It's a very small footprint because of our DFM automated method of packaging. All these factors, they come into play in terms of reducing the design complexity. It makes the whole system much, much smaller, makes it more efficient, more cost effective, and highly makes the whole system easily integratable within bigger systems.
Does Bourns offer any kind of reference designs for these solutions?
This transformer was specifically designed to work hand in hand with Allegro's HV8500 85040 chipset, as you can see there. So this is an amazing pairing. This is an isolated CAN-FET driver chipset with an integrated bias supply. So when you combine our transformer with this chipset, you get a truly self-powered isolated gate drive solution. What this means is that this is a cost-effective and highly integrated solution for isolated gate drive of CAN-FETs. So this is perfect for a wide range of solutions. So think of AC-DC and DC to DC converters, which kind of apply to a wide range of industrial applications, including transportation, robotics, and also a couple of critical grid infrastructure applications such as microinverters or solar inverters. So it's all about making your design process simpler and more efficient. And this reference design is a perfect example of how this actually happens in real life.
What kind of power topologies would this solution be a good fit for?
It's important to remember that different topologies and applications often require different power semiconductors and different components. So let's take a look at this circuit diagram here. So it showcases a typical half-bridge application using the Allegro chipsets we just talked about. So what's really clever here is that the chipset transmits both the pulse width modulated signal as well as the gate bias power through the external transformer that you see there, which is where our transformer would fit in. And what this does is it eliminates the need for any external gate drive auxiliary bias supply or high side bootstrap. So basically, this simplifies your design by a huge factor. And here's another huge benefit: because there's only one single magnetic isolation barrier transferring both the PWM signal and gate power, this significantly reduces the total parasitic capacitance between the primary and the isolated sides. Kind of a huge deal. So let's compare it with a typical solution using, let's say, a conventional isolated gate driver with a separate isolated DC-DC bias supply, where the capacitance from the DC-DC isolation transformer alone would be 10 PF or more. So this reduction in isolation capacitance does several critical things. So it greatly reduces the level of noise injected between your low voltage control circuit from those to high voltage, high switching nodes in the power stage half bridge legs. It also reduces system level common mode EMI, and it saves on power loss that occurs through repetitive charging and discharging of this parasitic capacitance. So it's basically a win-win situation for all power topologies.
All right. So, do you have any examples that you can share of this solution in a real world design?
Yeah, that's a good question. And we can actually look at a real world example of where this transformer really shines. So here we can see a block diagram which represents the various steps involved in converting solar energy into usable AC power. You can see that the main blocks of a typical energy harvesting and storage system is kind of the energy source, which in this case is the sun, and then the energy harvester where you see your solar panels. And then you see a high efficiency DC to DC converter, which is kind of a very important step. And this is one of the blocks where an isolation transformer would fit in. And then what you do with this energy, so you need a device to kind of store the energy, which is usually a battery, and then just to monitor the energy levels and to keep the power flow consistent and stable, you need a battery management system, which is BMS. Another major block, which is quite important, is an inverter, which basically converts DC to AC so that this solar energy that we've harvested, it's actually usable and we can use it for our day-to-day use. And finally, before we actually use this AC power, we need to condition it so that it's usable in different forms. So it can go directly to the grid, it can go into our EV charging units, or it can even be stepped down to wall boxes. So this is a great example of how our solution, specifically the SM91243L, plays a critical role within DC-DC conversion and inverter stage, ensuring that the power is safely and efficiently managed throughout the entire process.
Okay, so how do the different solutions in this family of isolation transformers compare?
Bourns, actually, we have a robust portfolio of a variety of push-pull isolation transformers, and these are suitable for a wide range of applications. Some of them we've already discussed, but also some of the more high-demanding, high-voltage environments as well. So the beauty of these transformers is that you can select the ideal transformer to suit your specific system design requirements, and it depends on a number of factors. For example, you would think about the creepage and clearance distance required. You would think about the high part isolation rating. You would think about the turns ratio. You would think about the primary and leakage inductance, working voltage, rated current, and so much more. So there's a lot of factors to think about. And all these factors, they come into play in terms of selecting the right isolation transformer. I would encourage our users to maybe visit our website for more information about these transformers, or you can even get in touch with us directly via our contact us page. And we can always help you design specific transformers for your specific requirements.
Well, I think that's all I have time for today. Thank you so much for joining me.
Thanks so much, Amelia. This was a pleasure. Thanks for having me.
And before we go, you didn't forget to click that link, did you? There you can find even more information about this topic from Bourns. For Chalk Talks, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, head on over to the Chalk Talk section of EE Journal. You can't miss it, it's right across the top. Or head on over to YouTube, youtube.com/EE Journal.